Hello, class. Sorry I'm late. We're going to continue our notes about bonding in solids. And just so you know, Moses, hi. Just so you know, tomorrow is Good Friday, so no class tomorrow. Pray. Pray for me, I'll pray for you. Think about God. Ask Him to protect us from all the bad things that are happening. Hi, Raksha. Hi, Temi. And I will finish chapter 11. When we come back on Monday, I'm going to start the chapter on acids and bases. Then hopefully if we get back together for school, I've been hearing rumors that there's not going to be any school till June. I'm hoping that's wrong. I'm hoping that hydroxychloroquine comes to the rescue, even though what you hear against it in the news media is, some people are saying yes, some people are saying no. I think it's actually effective based on some of the stuff I saw, especially if you look at the study that is being conducted by a doctor called Vladimir Zelenko. He's actually treating patients, and apparently he says anybody he's treated didn't end up on a ventilator. So that would be interesting to see. I got up to the point where we were talking about different types of solids. That there are 4 types of crystalline solids. We have molecular, covalent network, ionic, and metallic. So there's 4 types of bonds. So molecular is the weakest one. It's how organic molecules achieve the solid state. It's usually a combination of things like dipole-dipole or hydrogen bonding or London dispersion forces. The next is a covalent network, and covalent network is where every atom is connected to every other atom in its near vicinity, so it creates a big network. That's why we can say a diamond, which is a covalent network solid, is one molecule. When you're looking at a diamond, you're looking at one molecule because all the atoms in there are interconnected with all the nearest neighbors. Then you have ionic bonds and finally metallic bonds, and each one has its peculiar properties. An example of a molecular bond would be what you see with gases when they're solidified. So if you could freeze nitrogen, so nitrogen liquefies at -196. I don't know what its freezing point is. It's probably another 20 or 30 degrees lower than that, and then it turns into ice. But the only force holding the nitrogen atoms together is the London dispersion forces. It's a weak force, and that's why you got to really cool the molecules to get them to stick together. Then in a covalent network, you think things like diamond, things like silicon carbide, quartz. They're all super hard substances that are actually industrially useful. For example, grinding wheels can be made out of silicon carbide, and they're hard enough that they can basically take metal off a steel blade. So a steel blade, high quality steel, is about a 5 on the Mohs scale. Silicon carbide, I think, is around a 9. Only diamond is harder. And in fact, if you have a dressing stone for a grinder, it's a little diamond embedded into a screwdriver, basically. So it's the only thing that'll cut into a grinding wheel is a diamond. And diamond's a 10 on the Mohs scale. The Mohs scale is arranged so that each successive higher number can scratch the one below it. So if something's a 2 on the Mohs scale, it can scratch something that's a 1. If something's a 3 on the Mohs scale, it can scratch a 2, and so on, and everything below it, obviously. So something to scratch a knife blade made out of steel, which is a 5, high Sevier, you would need something that's a 6 on the Mohs scale. And to scratch a sapphire, which is 9 on the Mohs scale, you need a diamond. So a little bit about how they find out the structure of solids. Today's April 9th. Holy Thursday. Today Jesus instituted the Eucharist. Today's the Last Supper in the evening. So from page 471 of the text, it talks about X-ray crystallography. The structure of solids can be elucidated by shining X-rays. Through a high quality crystal. Why high quality? Well, because you don't want too many defects in your crystal, because that will spoil the results of your measurements. The diffraction pattern that results can provide information about the distance between atoms. X-ray diffraction is what was used to determine the structure of DNA and to determine that it was a helical, it was a spiral with basically two backbones. And by studying the information obtained by the spacing of different of atom layers within a solid, you can get an understanding of the 3D spatial arrangement of the atoms. After mentioning this on page 471, the book resumes its discourse of the forces between atoms. So on page 472, it talks about how the symmetry of molecules can allow for more efficient packing, and the closer the molecules are together, the more effectively those weak London dispersion forces can make the atoms adhere to one another. So, in a nutshell, if a molecule is asymmetrical, it might not pack as well, and therefore it'll affect its melting and boiling points. Asymmetry can disrupt packing of molecules by interfering with closeness, with, use a better word, proximity of molecules. So I'll show you the example the book gives. If you look at benzene, toluene, and phenol. Their melting points are Their melting points are 5, minus 95, and 43 degrees Celsius. So why this huge difference between benzene and toluene? Well, toluene has that methyl group sticking out, so it prevents the molecules from properly stacking the way they do with benzene. So it melts at a much lower temperature because those London dispersion forces only work very well at very short distances. And then if you add a hydroxyl group, which should disrupt the packing of the molecules, you would expect the melting point to be similar to that. But what else is happening here is that's the hydroxyl has a hydrogen. And with hydrogen and oxygen, you have the capacity of hydrogen bonding. So the hydrogen bonding more than makes up for the fact that there's a disrupting effect here. So it puts the melting point back up to 43. Boiling points, similar pattern. It goes 80, 111, 182 for the boiling points. So these are melting points. Boiling points are 80, 111, and 182. Yeah, 182 degrees Celsius. So it follows the same pattern, and for the same reason. Then we'll do the give it some thought on page 472. So it asks, which of the following substances would you expect to form molecular solids? Cobalt, C6H6, which is probably benzene, or potassium oxide? So the answer is that molecular solids are formed by substances in which the principal force creating solidification is usually one of the van der Waals forces. Like London dispersion forces, dipole-dipole, hydrogen bonding, etc. Only C6H6 would exhibit this property. Cobalt has metallic bonds. And potassium oxide is ionic. So in the case of cobalt, they have what's called the electron C model. The valence electrons have high mobility and they can be found all around the neighborhood of the atoms, but they create a bonding effect. And it also gives metal a property of malleability and ductility. They can be hammered and changed in shape. They can be stretched out to make thin wires. This is a property that is exclusive to metals. You cannot do that with ionic compounds. They just shatter. And then, of course, ionic compounds are held together by electrostatic forces because you have a positive ion and a negative ion and they attract each other. And it creates a matrix of alternating plus and minus charges. Now let's explore a little bit more about the different types of solids. We'll look at covalent network solids first. In covalent network solids, they consist of atoms held together in large networks or chains by covalent bonds. Some of the hardest substances we know are covalent network solids. So we got things like diamond, quartz, silicon carbide, and boron nitride. Are extremely hard and have high melting points. They're what you call refractory materials. They're able to withstand extreme conditions. And I was just thinking, as I was writing this, sometimes high extreme conditions can give rise to refractory materials, because the only materials that will withstand deformation of their solid form will be materials that have adopted the most stable and the most resistant geometric arrangement of the atoms. So it stands to reason that some refractory materials only form when you have extreme conditions. I'm sure if you went to the center of the Earth, you would discover some exotic crystals that don't exist at the surface of the Earth because the pressure is nowhere near high enough to generate them. At the center of the Earth, the pressure is something like 1,000,000 atmospheres. Right? The Earth is 8,000 miles across. That's about 12,000 kilometers. With a density of 5.5, it's equivalent to 6,000 kilometers of depth in rock at 5.5 would give you about 30,000 kilometers of depth in water, so 30,000 atmospheres. So 30,000 atmospheres times 14.7 pounds per square inch gives you 441,000 pounds per square inch. I was a little bit off. So actually, I was off by a factor of 2, but 441,000 pounds per square inch is my estimate of the pressure at the center of the Earth. So you can get some, I'm sure you get some pretty freaky things forming at those pressures. The density down there apparently is something like 25. There is no material that we know that has a density of 25. The densest material we know on the surface of the Earth is iridium, and it has a density of 22. So how do you get a density of 25 if the densest element only has a density of 22? It's because there's some altered states of matter down there. You have, they always teach you that solids can't be compressed. Well, that's not exactly true. You can compress solids, you just need a lot of pressure. And I think 440,000 pounds per square inch qualifies as a lot of pressure. So what else can we say about these? Graphite is also a covalent network solid. Graphite is composed of layers of interconnected hexagonal rings. Hexagonal rings. The layers can slide over each other. Making graphite a good lubricant. It's also, believe it or not, a conductor. It conducts electricity. pencil lead conducts electricity. I even have a demo of that in one of my videos. Now let's look at ionic solids. They're also quite interesting, and they make a range of very useful materials also from a technological standpoint. The strength of the ionic bond is predicated on two things: how close the atoms can get and how much charge they carry. So if you have a highly charged particle that is also very small, then the particles that constitute the ionic compound, which is a plus charge and a minus charge, can get really close together and they'll form a stronger bond. So ionic solids are held together by electrostatic force between charged particles. So the greater the charge, or the smaller the ions, then the stronger the crystal is. Just to give you a little sampler, let's look at this table of melting points. So, sodium chloride, magnesium oxide, boron nitride, and hafnium carbide. So this is made of plus ones and plus minuses. This is made of plus twos and minus twos. Boron nitride is made of particles that have plus 3 and minus 3, and hafnium carbide is plus 4 and minus 4. Okay? Melting point of sodium chloride, 801 degrees Celsius. Melting point of magnesium oxide, 2,852 degrees Celsius. Melting point of boron nitride, 2,973 degrees Celsius, and the melting point of hafnium carbide is 3,890. So you see a definite trend going upwards. The jump here is not as spectacular, but it's arguable it's because the particles also get bigger. Look at hafnium carbide, 3,890. That's what they use as a liner for steel smelting furnaces, because it can hold molten steel without degrading. So that is, hafnium carbide is the material that has the world record for having the highest melting point. It is what you call a refractory material. I'll give you a nice definition for that too. Refractory. A refractory material is resistant to decomposition. By heat, pressure, or chemical attack. And retains strength and form at high pressures or high temperatures. So an example is the hafnium carbide bricks are used to line the inside of smelting furnaces because they can contain molten steel, which has a melting point of 1,375. So you got a nice 2,000 degree margin before you get to the melting point of the hafnium carbide. So the structure adopted by ionic solids depends on the charge and the size of the ions. For example, sodium chloride has a primitive cubic structure. Zinc sulfide has a face-centered cubic structure, and calcium fluoride has a face-centered cubic. So NaCl has 6. Zinc sulfide has 4, and calcium fluoride it's not clear. It says in the book that there are twice as many fluoride ions, gray, in the unit cell as there are calcium fluoride. Okay, so it's a 2-to-1 ratio. You can see the picture on page 473. If you look at metallic solids next, now metals make the bulk of what we call useful materials because there's a metal with properties appropriate for just about any technological application you can imagine. So we exploit those things very much. So it consists entirely of metal atoms. Usually hexagonal close packed. With an FCC or BCC arrangement, face center cubic or body center cubic. That's, you can look at the notes from a couple days ago, with 8 or 12 as coordination number. So this is on page 475. It's bonding due to valence. Electrons. More valence electrons means increased melting point, which means the bond strength is usually also higher. And also because of the fact that these valence electrons are mobile, highly mobile, metals conduct heat and electricity. I'm going to show you the answers I've worked out so far. You can do this over the next 3 days, Friday, Saturday, Sunday. So this is one page of work. I'll show you the questions that go with it. We're not going to belabor this. So here's the bottom of the page. And I mean, you have the textbook, so you can see for yourself, just so you recognize it. Try those 2 pages for homework. I'll show you my answers and my notes. Why not? Here's the notes. I don't already have them. From page 9, top of the page. Page 9, bottom of the page. Page 10, top of the page. Page 10, bottom of the page. And then my answers to the, no, those are still notes. Page 11 of notes. Bottom of page 12 notes. Sorry, that was bottom of page 11. This is the top of page 12. Bottom of page 12. top of page 13. And these are exercises. These are the answers to the exercises, bottom of page 13. And I got up to page 14. Top of page 14, bottom of page 14. I will see you on Easter Monday. Have a happy Easter.